For this example, we want to find the general solution to the differential equation y double prime plus 2y prime minus 3y equals 0, and verify that it is a general solution. So to do this, we first need to find two solutions from somewhere. And how do we get those? Well, we guess those with our guess of e to the rt, and looking for what values of r make that work. If I plug in e to the rt, I'll get an r squared here, an r here, and nothing here. We'll end up with an r squared e to the rt plus 2r e to the rt minus 3 e to the rt equals 0. I can cancel the e to the rt's. And then I'm left with r squared plus 2r minus 3 equals 0. This factors as r plus 3, r minus 1. My two values are r equals minus 3 and r equals 1. So that gives me two solutions of the form y1 of t equals e to the minus 3t, and y2 of t equals e to the t. Now, if all is good with this, our general solution should then be y of t is c1 e to the minus 3t, so c1 y1, plus c2 e to the t, c2 times y2. Now we have to verify that this is in fact a general solution. How do we do that? Well, we look at the expression y1 of t, y2 prime of t, minus y1 prime of t, y2 of t. And so in this case, let's just plug this in. y1 is e to the minus 3t, y2 prime is e to the t, minus y1 prime is a negative 3 e to the minus 3t, and y2 is e to the t. This is e to the minus 2t plus 3 e to the minus 2t, or 4 e to the minus 2t. That's never 0. You could also have plugged in t equals 0 or t equals any number to get a non-zero answer to verify this fact. Since this is non-zero, we have a general solution. So our general solution is exactly this up here. If we were then given an initial condition, we could then plug that in to figure out what C1 and C2 have to be to meet that condition. One more slight expansion on this part is that this same process works for whenever this quadratic here has two distinct real roots. So if the quadratic factors as r minus r1 times r minus r2 equals 0, we will get e to the r1t and e to the r2t as solutions. If we plug it into our expression here, y1, y2 prime minus y1 prime, y2, this will become, if this is y1 and this is y2, this will become e to the r1t times r2 e to the r2t minus r1 e to the r1t e to the r2t, or r2 minus r1 e to the r1 plus r2t. So as long as r1 is not r2, this is not a double root, but it's actually two separate roots, this will never equal 0. So let's get the general solution. This idea here is also why we just know this method always works for any case where we have two distinct roots. If I have two distinct real roots, this process will tell me this always works no matter what. So all I have to know is that I have two distinct roots, and then I will know for a fact that's how I get my solution. I find those two roots, I put them in exponentials like this. I know that this term here will never be 0, therefore I have a general solution of the form y of t is c1 e to the r1t plus c2 e to the r2t. And so that method will always work to give us a solution for these problems when I have two distinct real roots of my equation. If I don't have those, that becomes a different story. That's where I then need to do things with complex numbers or other things where the roots are the same, and those will come over the next couple of sections. So for this case, this is the way you set up and handle the situation when you have two distinct real roots to this characteristic equation here. Here we have minus 3 and 1, and that is a general solution. It will always work when those roots are real and distinct for the second order constant coefficient homogeneous equation.